Hello, today we are going to start talking about matrices. So, the first thing that we need to do is look at what a matrix is. So, essentially, it's like a mathematical table. All right. So, our structure and notation, we're going to, for these tables, talk about them in terms of naming them with uppercase letters. So, for example, we have matrix A, and sometimes we also use lowercase letters, but we will either state the size somewhere or just say like 2 by 2. So it'll be 2, comma 2. So our first one is the number of rows. The second number is columns. All right. And for each individual location, we have 1, 1 is this section, this term is in the first row, first column. This 1, 2 is in the first row, second column. Okay, so we've got rows by columns. So if we look at a matrix like this one, it has 2 rows and 3 columns, so it's a 2 by 3 matrix. This one, say we have something like this. This one, it has 4 rows and 1 column, so it's a 4 by 1 matrix. We can do specific row operations on a matrix, and that is something that's legal to do. So we can switch any 2 rows. So this is where we interchange row 1 and row 2. All right, and that is something that is valid to do on any matrix. Multiply a row by a non-zero constant. So row 1 becomes 3 times itself. All you do is take each term and multiply it by the scalar. So think just like vectors, we have scalar multiplication. So this would be 3 row 1 would become row 1. All right. And then you can add 1 row to another. And this is something that's going to be helpful when we start applying this in a later lesson. Some of the things with matrices, and these are the ones in your assignment, are straightforward. So we're not going to look at those specific ones, but ones that are similar to this. If we're adding 2 matrices, well, this is a 2 by 3 matrix. This is a 2 by 3 matrix. Since they are the same size, we can add them. So if we're adding them, all you do is add the terms that are in a specific location. So we've got this first row, first column. We add the 2. So 6 plus negative 3 is 3. Second row, first column. Second row, first column. So 2 plus negative 6 is negative 4. First row, second column. So 6 plus negative 1 is 5. And then first row, third column, 2 plus negative 1. And then you do that for every position in the matrix, and that is your result. You can only add or subtract 2 matrices when they are the same size. Now, 4 here takes a look at our scalar multiplication. So think exactly what we would do with vectors or with anything else you would think of where we're multiplying by a constant. All you do is take the scalar and multiply that constant by every term. So our result then is going to be 25 in the first row, 5 in the second row, and 15 in the third row. So it works exactly the way that you would think it would. Now, multiplication of 2 matrices is something that's a little more challenging with this. All right, so you can do any of these addition ones or scalar multiplication, no problem. But when we have something here, that's going to be a little trickier. So, and this row operation is in there too. Just follow the directions. You're just multiplying all of the terms in row 2 by 3. And there's your solution. So when you are multiplying, what you need to do is you're multiplying row by column. All right, and this diagram is something that is helpful to take a look at. So row by column. So this first row, first column, we're taking your first row, multiplying it by your first column. So think how you'd find the dot product for a vector. So what happens there, you do row by column. So you do 1 times 3 plus 7 times 5. And that is going to be in this position. Then, when we look at what needs to go here in our first row, second column, we take our first row, multiply it by our second column. So it ends up being first row, second column. So 1 time, oh, why is that not yellow? Let's try that again. Okay, so it's 1 times 3 plus 7 times 2. This same thing is going to happen for each of our spots. So here we've got our second row, first column. So second row, multiply it by our first column. So it will be 2 times 3 plus 4 times 5. And then for our second row, second column, we do second row multiplied by second column. So it will be 2 times 3 plus 4 times 2. So it's going to share some characteristics with finding dot products for vectors. So each location is just going to be essentially the dot product of the row and the column that make up that section. So this one is, its location is 1, 1 because it's in the first row, first column. So you multiply the first row by the first column. This one is in the second row, or sorry, first row, second column. So we multiply the first row by the second column, and so on. So when we go through and simplify that, so we have 3 plus 35, so that's going to be 38. 3 plus 14. 6 plus 20. And then 8 plus 6. So there is our product of these matrices. Now, as far as size of these matrices go, if they're the same size, we can multiply the matrices. If they're not the same size, we can still multiply them. And we'll look at that in just a second of how that happens. But it has to be like the number of rows has to be equal to, or the number of rows in the second matrix has to be equal to the number of columns in the first. So think about it this way. Like we've got a 2 by 2 matrix that we're trying to multiply by a 2 by 2 matrix. These two numbers match up. So that means that we can multiply the two because we need to multiply rows or like columns here by the number of rows here. So our result is going to be a matrix that has this many rows, so the same number of rows as the first matrix, and the same number of columns as the second matrix. So matrix multiplication is not commutative. A times B is not equal to B times A. So let's take a look at multiplying C and D before we do ones that are different sizes from this. So CD, we go in here, since C's 2 by 2 and D's 2 by 2, like we found over here, our result is going to be a 2 by 2. So we multiply row by column. So 2 times 1 plus 1 times 3. So that one's going to be 5. We go through, we multiply over here, we've got row times column. So we've got 2 times 4. It's 8 plus 1 times 6 is 14. Because it's in this location is the first row, second column. So we multiply the first row by the second column. So then what we do is, for this location, it's second row, first column. So we take second row, multiply by first column. So 5 times 1 plus 2 times 3. Then last, what we do is for our second row, second column, so we take our second row, multiply it by our second column. So 5 times 4 is 20, 2 times 6 is 12. Add those together, we end up with 32. So then let's take a look at multiplying matrices that are two different sizes. So we need to check first to see if this is even possible. So write out your sizes first. So M, it's got 2 rows and 3 columns. N has 3 rows and 2 columns. Because these numbers are the same, the number of columns in M is the same as the number of rows in N, that means we can multiply them. And our result is going to have 2 rows and 2 columns. Okay, so it's just going to be a 2 by 2 matrix. And we solve for these locations the same way that we would do it with a 2 by 2 matrix. So we take our first row by our first column. So 2 times 4 plus 8 times 6 plus 3 times 2. So 8 plus 48 is 56 plus 6 is 62. Then for our first row, second column, we take our first row, multiply it by our second column. 2 times 1 plus 8 times 3, so it's 26 plus 12 is 38. So it's just like finding the dot product. Multiply the first by the first, second by the second, third by the third, add it together. So then when we're looking at this location, second row, first column, we multiply our second row by our first column. So 5 times 4 plus 4 times 6 plus 1 times 2. So we end up with 46. Then for this location, because it's second row, second column, we multiply our second row by our second column. So it's always row by column. And we're finding dot products. So 5 times 1 plus 4 times 3 plus 1 times 4. So it is 21. So our resultant vector is a 2 by 2. So that's Mn. If instead we went through and multiplied the other way, n times m, well, we need to check to see if we would be able to do that. So we'd have a 3 by 2 matrix, because that's what n is, by a 2 by 3. These numbers are the same, so we would have a valid matrix multiplication, but our output would be a 3 by 3 matrix. So our matrix multiplication is not commutative. We will continue on next time talking about more matrix multiplication and where this comes into play. But for now, thanks for watching.